Welcome back. I hope you all had a nice winter break. Welcome to the first seminar of spring semester. Before I introduce our speaker today, I just wanted to get you guys excited for the speakers that we have lined up this semester. Keep your Thursday afternoons open. I had a number of recommendations from all of you for speakers, including our speaker today, so thank you for that. We also have Matthew Bracken and Brian Gaylord, who are recommended by a couple different folks here. I've invited a number of early career scientists, many of whom I've met through National Geographic. So next week we'll have Roxanne Beltran here. She's a Nat Geo explorer at UC Santa Cruz who looks at elephant seals. And then later in the semester we have Dr. Erica Woolsey. She was in a Forbes article recently as the Laura Croft of the ocean. So she's doing some really cool work with an organization she developed called the Hydros, using different technologies for ocean education. We'll have Claudie Boulet, who's a new professor just down the road at UC Santa Cruz, doing climate change studies. I'm presenting March 21st, so if you haven't seen me around this month, it's because I've been hiding out in the lab doing mercury chemistry. So I scheduled myself a little bit later in the semester so I can share with you an update on some of the work I've been doing with mercury and microplastics. And then finally, we're going to have Carolyn Box, who is the science director of 5 Gyres Institute. So she sails around the world, sampling microplastics in all of the oceans. She taught me how to sample microplastics in San Francisco Bay, so I'm excited that she'll be joining us. And just a reminder, I'm also responsible for scheduling fall 2019 semester. So if you guys have more ideas or suggestions, feel free to stop by or send me an email. Okay, today we have with us Dr. Craig Jones. Craig has a PhD in ocean engineering from UC Santa Barbara, and he works at Integral Consulting in Santa Cruz, where he's been since 2014. He has 20 years of experience developing engineering projects to characterize offshore environments. He works in rivers, estuaries, and coastal systems. And today he's going to share with us some work on sediment contaminants in a wetland, Barry's Creek in New Jersey. So, thank you, Craig.
Thank you very much, Caitlin. I haven't talked yet. You guys might not want to applaud yet. But I'm impressed. The pizza with the seminar, that's awesome. What a great way. We didn't get that at Santa Barbara. We were lucky to get anything, so we just really had to want to be there. So I'm going to try to make this exciting enough to make you want to be here. And I'm honored to be here for the first talk of the semester. So thank you, Caitlin. Thank you, Marcel. Thank you, Ivano, all you guys for helping get me in here. And I've been in Santa Cruz working in consulting since about 2002. And I came out of a postdoc kind of wondering where I was going to land and what I was going to do. And academia was really interesting to me, but it was a little scary in some ways, seeing what some of my colleagues were doing. So it worked out that I kind of had a chance to try it on. And it's been interesting. We built a practice with our group in Santa Cruz where we kind of have 1 foot in research and 1 foot in applied science. So we do about half our work is for government agencies. We do work for EPA, Department of Energy, Department of Defense, all around environmental research. Marine renewable energy is a big area we're working in, to industry work where we're helping them, this particular project that I'm going to show you, helping them figure out how to clean up environmental problems. And surprisingly, we hear so much about the bad side of what industry is doing. You'll see what was done here through industry funding, trying to figure out the right way to approach one of the most mercury contaminated sites in the United States and world, actually. Also, PCBs are thrown in there for good measure, dioxins, copper, arsenic, a few other things. And based on that lineup, you can guess where it is. It's in lovely New Jersey. So there is the Hackensack River coming through. The Passaic River right here, which is heavily contaminated with dioxins due to the production of Agent Orange during the Vietnam War. Newark, lovely Newark, is right down here. New York City, of course, everyone can recognize Manhattan. So this was a heavily industrialized area. This is where the Giants play football. So that is, I forget what the name of their stadium is now. I don't know, they've changed the name of it, whatever company owns it now. Here's the Hackensack River. The blue are subtidal channels connecting very broad Phragmites Marsh. There's a secondary channel here. I call it secondary now, but this originally was the original channel for Barry's Creek. It used to be cedar salt marsh, so it was heavily freshwater dominated. But as they opened up the Hackensack River, Newark Bay, the Passaic River, dredged them for shipping, that allowed the salt wedge to come much further into the system. As that environment changed, these became broad, intertidal Phragmites Marsh. So it was a big change in about 1900 in the dynamics of the system. So it was a big change in the ecosystem. So now you have very stable Phragmites Marsh. Everything in green is basically Phragmites. You can see some of the secondary channels that are connecting a lot of the Phragmites Marsh in here. But the only thing that's subtidal all the time is basically what's in blue here to give you an idea. So up at the head here, we had some industries that were pumping out a lot of mercury. We had some industry here that was pumping out a lot of PCBs. And then the rest is just New Jersey. And I say New Jersey, but there are lovely parts of New Jersey. This particular part is not one of them. However, actually, once you get into the upper system, the Phragmites marshes are kind of cool looking. I mean, it's a neat system. This is one of the tide gates that goes to an upper tributary that feeds fresh water into the system. But again, this is a brackish water system. It is not freshwater dominated, so we're not looking at like a stratified estuary. Historic contaminants, as I mentioned, mercury PCBs, extensive Phragmites marsh, highly urbanized. And right now, this is designated as a Superfund site by the EPA, so it's going through the whole Superfund process. And where it is right now is that there has been a proposed remedy that is being reviewed by everyone, and eventually that remedy will go into play. But this mudflat right here has, just to give you an idea, these mudflats on either side of this are like part per 1,000 mercury, total mercury. So anyone who deals in mercury chemistry knows that's like screaming high. In fact, the highest in the US that I've ever seen. And I say that because we worked on a site in Italy that was actually higher. But what am I going to talk about today? So we're looking at how do we accurately describe transport in the system so that we can figure out how to clean it up. Where is the mercury in PCBs moving? Where is it coming from? Where is it moving to? How can we shut down those transport processes to really reduce the risk? We can't go in and dig out all the marsh to clean it all up, because if you do that, then you've just destroyed all the habitat you're trying to save and you're never going to get back to it. I say save because that habitat has changed. We're never going to get back to salt cedar marsh, but we want to preserve what's been there for at least 120, 130 years. Because that's become valuable habitat for the area. So we want to look at the short-term transport processes important for driving mercury. We want to look at storms, see what happens during storms. But we also want to look at long-term. How is this system recovering? So typically these Phragmites marshes are depositional areas. They trap a lot of sediment. You saw how dense those stands of Phragmites are. So you can imagine the water just barely trickling through. It's going to trap a lot of sediment. So those end up being good sediment accumulators. The question is it accumulating fast enough that we can reduce risk in a reasonable time frame, which is on the order of 10, 20 years. Also, what areas might not be recovering? Where do we have areas that are dynamic that still have mercury in them? And those are areas we might want to target for active remedy. So I've talked about this a lot, so I'm going to move on because I tend to talk way too much on this system because it's an interesting one. So what kind of processes are we looking at? Here we go with our tidal exchange of sediment. So we'll get sediment in from the estuary. We get little pulses of sediment in from the upland, but primarily the estuary is the big source of sediment. So that tidal exchange will bring it in. We have our channels that'll advect those sediment around. Eventually it'll get deposited up on the mud flats on a daily cycle of tidal deposition. And eventually we get the spring tides, which really activate into the marsh, and we get a net import into the marsh. So as our solids go are typically where our contaminants go. One of the reasons we have these sites that are still contaminated 50 years after we dump stuff in there is because these contaminants are hydrophobic or associate with the organic material, which is also typically what drives the ecosystem risk. So what's happening on the organic end? because we are concerned about the organics. And anyone who's doing work here in the slough certainly knows that the organic picture gets really complicated when we're talking about salt marshes and tidal wetlands. So we have organic material generated all the time by the Phragmites, right? We're going to have basically shedding of that, which is going to be labile and refractory is what the L and R are for particulate material. So we'll have our labile material that really moves really far. Get down, it'll get into the bed, it'll break down. We have refractory material following and coming into the marsh as well and being back up taken into there. So we have a big source of organic material. Now, if the mercury is also moving around in here, how that mercury associates with that organic material is really important to not only the movement of the mercury, but the methylation of the mercury as well, and what's going on with the geochemistry. I'm not going to dive into that today because we got a lot of other cool stuff to talk about. So let's take a look at what's happening on a daily basis with the sediment in this channel. So what we did is we put platforms throughout the system. We had ADVs that are looking down near the bottom, so we're looking at the turbulence right near the sediment bed, but also looking at the backscatter from those ADVs to look at the amount of material in the water column. So we can correlate that to suspended solids, so we can get measures of particulate concentrations. We can get the shear stress from the ADV velocity. We can calculate a Reynolds shear stress from that. We have the velocity, of course, and we have a depth. So I'm going to start at the top. Here's our tidal signal. It's a very similar tide to what we have out here. It's a semi-diurnal tide, so it's about a 2 meter max tide. And here you can go, we see we're going from about a 3 meter depth to a 5 meter depth. So this is a site that's a moderate depth in this system. We have the high slack tides in the blue here, and in the orange we have peak flood and ebb tides, or high and low slack in the blue. So blue is mellow, high slack, low slack, and the orange is higher velocity. So here is the zero velocity. So here we have peak flood velocities, peak ebb velocities, and so on throughout this day. You can see we've been working on this system for years. This was one of our first years that we were in the water in 2011. So shear stresses are high when velocities are high. That's not a big finding. However, it is good to see the distribution of sediment as we're seeing these flood and ebb. So one of the things we can start to look at with that is what's our net direction of transport. So we can start to look at cross-sections throughout the channel to look at fluxes of sediment in different directions, and I'm going to show you guys some summations of that in a little bit. But I'm going to go back to cartoons because it's really important to get our conceptual model, because we can go out and spend $1 billion getting the best measurements in the world, but it's always important to kind of ground it in a cartoon. So there's what's called the fluff layer, which is kind of our very light consolidated material at the surface. And it's funny, I see a few of you giggling back there, I hope at the fluff layer comment, but we got a lot of, you can imagine talking to a bunch of people from like Dow Chemical and our place. They're like, here's the fluff layer that moves your contaminant around. They're like, oh yeah, these guys are a bunch of jokers. So we had to dive into the literature and give them the whole like precedent of the use fluff layer for this fine layer that's on the order of a couple of millimeters thick, but it only takes a couple of millimeters of resuspended sediment to be 100 milligrams per liter in the water column. So you can get a lot of turbid water or high particulate concentrations from very thin layers of mobile sediment. And it's very common in estuaries to have this mobile layer of fluff. Like Rocky Geyer, if you guys know his work, he calls it the mobile bed. I like the fluff layer a little better because a mobile bed insinuates that there's this huge mass of sediment. It is a finite mass of sediment, but it's a very small mass of sediment. But you see the signal of it all the time. Now then, my favorite word that I learned on this project how to pronounce is autochthonous. And this took me about a year to actually be able to pronounce that right. But this is, so we have our normal sediment moving around, which is our inorganic sediment coming from the estuary, everything else. There's a little bit of plankton production in the estuary, but it's actually a fairly small percentage of this. But this autochthonous material, which is created inside of Berry's Creek, This is the material that's coming off. This is that shedding from our Phragmites. It is a big load of solids material to this fluff layer. So that was an interesting finding here, that as we look through the literature, autochthonous organic material production is a well-known process. However, when you start talking to the physical transport people, it's almost never included in models and measurements, and they never really tease it out. It was a huge thing here, looking at the difference between the organic material motion and the inorganic. The organic material in the water column often made up 20% of the solids, and that's huge. I mean, if anyone looks at estuarine solids transport, it's usually on the order of a few percent. It's very minerogenic in most estuarine sediment. And high organic material concentrations in estuarine sediment are about 6%. But these are big. These are much higher. So what does it look like? We got this cool tool called the spy camera that we can drop down to the bottom, and it shoots a prism into the mud and takes a side picture like this. So we have hundreds of these throughout. And pictures are worth 1,000 words because you can see a lot going on in here. Biologists can see a lot that I can't see. I'm more of a physical guy, so I'm interested in what's happening and just the physics of it. So we have good high-resolution image. We can do particle sizing on this, but we can see here our fluff layer, a very light consolidated layer. We see a more heterogeneous, oxidized, and consolidated sediment. These are worm tubes. So there is some smearing on the window, but we do have worm tubes that you can see they're mixing down the oxidized sediment. And then we get to our deeper consolidated sediment that are anoxic. So this starts to tell us a lot. You can do so much core logging, it'll make you blue in the face and line that up with chemistry, but at the end of the day, that's all going to be finite. It's really cool to be able to link it with imagery like this, in situ imagery like this. So the final thing that we did to really get a big picture on it was we had permanent platforms in on these fancy pilings at locations at each mouth, the mouth of each entrance, here just above the confluence of those two channels in the middle system, and one in the upper system and one in the way upper system up here for 2 years. So we had 2 years of continuous measurements, bottom-mounted ADCPs. That's when it was brand new and it went in the water. It did not look like that after 2 years, I can tell you. So those were sitting on the bottom. We were able to get, we had water quality sensors in here too, getting a full range of everything from backscatter to obviously pH, conductivity, the standard suite, but we also had chlorophyll A in there to look at living or dead organic material. We had a few other fancy optical instruments, but I'm going to talk about the optics in a little while. So I'm going to talk about the hydrodynamics because I want to get at the overall circulation, because if we can look at the overall circulation, then we can dive deeper into how the contaminants are moving around, how the sediments are moving around. So let's build a numerical model. So we can take this digital elevation model, which is a combination of LiDAR, multi-beam bathymetry in the channels, and yeah, that's a narrow channel to do multi-beam in, but we managed to get that in there. Single beam in some of these other channels. Blended it all together, did a lot of ground truthing through these marshes to correct the LiDAR for those big 6 to 8 foot stands of Phragmites. Built 5 to 15 meter grid throughout the system so that we could simulate the hydrodynamics. We had a ton of that data to validate with, and does anyone in here do numerical modeling? I'm not going to dive in too much if you guys don't. Anyway, we had a lot of data. We validated it, which is really good because numerical models are complete BS unless you have good data to drive them with. I started out as a modeler, so I say that from a person who spent their whole PhD working on developing numerical models and then spent the next 8 years of my life in the field because I didn't believe any of the models. So we did some dye studies to also help validate some of the mixing in the model. So this is the upper system. This is way in the upper system. So we come here down that main channel here. We released dye in the upper system during 2 different events. So we got to look at a very dry event during neap tide. So that would be your lowest mixing situation and the lowest transport you would expect to see. And then a spring tide, we happened to get a good 2-inch rain event as well. So we had a rainy event. This is what the dye looks like. But at all those platforms I showed, we had sensors so we could see the signal from the fluorescein dye, but also did synoptic measurements, ran up and down the estuary in a boat so that we could see how that dye was distributed. The cool thing is, and I'm going to show you here, I'm going to have to explain this a couple of times while it's running. Here is the dye on the left-hand side, and this is from the computational model, which actually agreed fantastic with the dye study. This right here is shear stress in the channels. So red is high shear stress, blue is low shear stress. I focus a lot on shear stress with sediments because high shear stress means a lot of sediment transport. You have a lot of shearing on the bottom, that's what picks up sediment and move it around. The low shear stresses are areas that are going to be more prone to deposition and collection. So that's why you're going to hear me throw around shear stress and be concerned about shear stress a lot. Up here you have the tides during this study period, and the dashed line is the rain event. So there's a small rain event here, a little rain event here, a little one here. You will see the dye releases come right there. So that was right before the event. You can see the plug of dye dispersing very quickly during this event. And that's because we had rainfall coming in and we had spring tide that really dispersed it fast. As we come to this one right here, which I'll flip back around in a minute. Okay, we'll see another dye release here. This is during a neap tide, so you'll notice how much that stays much more in the upper system and really makes it into this middle system, right about to where we had that platform there. So one of the things we saw is the system is really divided in half in a certain way. There's typical conditions, mix things in this upper system and keep them in the upper system. Only during the big rain events that we'll see in a bit do things get washed all the way down to the lower system. Now that's good news because where was most of the contaminant released into the system? So the good thing about that is we see a lot of the contaminant up here, most of it stays up here. And there's a natural separation from what's connected to the estuary down here. I by no means want to insinuate that Hackensack is clean, but fortunately this wasn't a huge source to the Hackensack. But let's take a look at that. So you see now with the rain event, this one makes it much further down, much quicker, and actually in 2 tidal cycles reaches out to the river. So I do have a point to all this. So one of the cool things we can do is we can look at the mixing between the upper and lower system. So here's our upper system at 0, and this is meters down, so 6 meters down to the Hackensack River. So this is our river boundary, and this is our upper boundary of the system. We call it's West Riser Tidal Gate, was that tide gate that I showed you guys earlier. And that's where a lot of the fresh water comes into the system. So what we can do is in the model, now that we have a good model, is we can release dye up here, and we can release dye at this end, and we can see how far they mix on average over a few tidal cycles. So what that tells us is kind of where natural breaks are in the system. So this is very low rainfall, so there's not much fresh water coming in, which is a lot of the time. And the natural break is only about 1 kilometer down. So this gives us an idea of how far transport we would expect from the contaminant sources. But it also gives us an idea how much transport we get from the estuary of sediment too. So sediment, again, is our recovery mechanism. That's what's going to help us cover up the contaminant. So that's kind of not so great that they don't cross over that well. As we get to bigger rain events, you can see that things are pushed further down in the system, and we get some mixing up from the estuary. But one of the neat things, I'm going to show you this waterfall graph. This is a whole year. Here's our rainfall events. This is the upper system, so this is where rain would come in. So this is distance on this plot, and this is time on this plot, and the color is total suspended solids. So this is one of the ways we're looking at sediment sources into an estuary. So, and if you guys know about wetlands, those of you who are studying wetlands, wetlands live and die by sediment supply. And certainly out here, Elkhorn Slough is a perfect example of that, of the big changes going on when you screw around with sediment supplies. So one of the things we really wanted to understand was sediment supply. So what I'm showing here is every time we get a rainfall event, we can see pulses of sediment come in from the upper system. The other thing we're seeing is these slightly elevated TSS levels coming in every 2 weeks or so. So that's our spring neap cycle, tide cycle. So during neap tide, the system doesn't have a lot of sediment moving around. As we move into spring tide, sediment's coming further and further up into the system, and then that goes back. So the estuary is an important part of this. However, when we get these big rain events, well, it's only a 1-inch rain event, we get big plugs of sediment coming into the upper system. So that starts to tell us a lot about what's happening. So let's pull that together to long-term transport. So I talked about accumulation rates, and we're really concerned about how sediment's accumulating in different areas. So we have radioisotope cores. So we could go in and do cesium and lead-210. Cesium worked a little better in this system than lead-210 because of all the vegetation kind of messes up some of the surface lead-210 profiles. But we can look at the cesium peak. I'm assuming most folks are kind of familiar with radioisotope or geochronology. So we're looking for the cesium peak that was created by radioactive testing, and it's an atmospheric fallout. We can still see those cesium signals. So it gives us a really good marker. The horizon of those is about 1958. The peak is right about 1958. And when did the treaties start that ended? It was 1964, I think, is when we generally see it taper off. But it's a really good marker in sediment in depositional systems. So from that, these tiny numbers you can't see, and you just have to take my word for it. What we see is in the marshes, we see on the order of about 1/2 centimeter per year, from about 0.1 to 1/2 centimeter per year, so 1 to 5 millimeters per year throughout the marshes. In some of these mud flats, we're up to 1 centimeter per year over. So the mud flats tend to be really good accumulators. They are good sticky buns for sediment. But the marshes are a little bit slower, so it makes sense. You come in with the tide, you drop out your biggest sediment load here, so you have your highest deposition rates. As you get further in, there's not as much sediment available for deposition. So that's kind of your classic salt marsh deposition model. And then some of these center channel areas, we don't see much deposition at all. That's a stable channel that's just a thoroughfare for our sediment. So what can we do to look at that? So remember all those platforms I was telling you about that we put throughout the system? We made a really complicated graph out of them. So I'm going to attempt to explain all the arrows, but they will make sense when I get through it. So all these guys are the upland input. So that's all of our tributaries in the system that bring sediment in. NT is metric tons of sediment. The red arrows are our advective load of sediment. So that's how much sediment is moving through when we get those big pulses during the rainstorms and stuff. The blue arrows are what's coming in from our tidal load. So essentially we can see tidally and advectively what's happening. The difference here at the mouth is more sediment is coming out of here than is coming in. But there's a catch to that because we have these upland inputs too. So we could take any two of these cross sections and add all these numbers up and figure out what's depositing. And if you notice, all of these are depositional. So that upland load minus what's going out advectively minus or plus what's going in tidally gives us how much is accumulating. So that's kind of our first cut at looking, all right, where are big areas of accumulation? Where can we be losing sediment? Thank goodness we're gaining sediment in all these areas. Nice, healthy salt marsh. As we expected from that result I just showed earlier, we have a lot of sediment coming in from the estuary in the lower system that drops off, and then eventually we actually only have downstream transport of sediment in the upper area, and the whole sediment load is coming from upstream. So does that kind of make sense? Even though it's a crazy complicated graph. So where are we going with that? So now for the different parts of the system, we can calculate what's called a trapping efficiency. And we do this for reservoirs all the time. But we can look at the trapping efficiency in each of these areas, and they're only on the order of 4, 5, 6%. So even though there's like thousands or hundreds of metric tons of sediment a year trapping, that's still only a few percent of the sediment load. just to give you an idea of what's moving around tidally every year. I mean, it's like thousands and thousands and thousands, and well, I guess that'd be like tens of thousands of metric tons, actually probably 100,000 metric tons. But one of the things we're trying to do here is validate our model. And the important thing about validating the model and saying that, yeah, our model is doing the right thing is this. Now we can use our model to make maps like this. If we have, this is estuary sources of sediment and upland sources of sediment. So with the estuary sources of sediment, we can look at what percentage of the material depositing is made up from the estuary. So anything that's bright yellow is mostly sediment from the estuary in this plot. And anything that's blue is not stuff that's coming from the estuary. Vice versa, here's stuff coming from the uplands versus the estuary, which is blue, of course. So what can we do with this? Well, let's say I have a lot of contamination back in this little reach here, which we do. What are we going to do about it? So we know the upland sources of sediment are really important, really critical to that. So we want to make sure and not screw around with those upland sources of sediment. What can we do as far as a remedy that might enhance that? Well, maybe we can place some extra sediment there to kind of put it on steroids a bit and help the recovery in those areas. An area like this, like we have a strong estuarine, that's really nice, clean sediment that's coming in. An area like this in the middle and some of these mud flats that aren't really getting sediment from everywhere, well, we need to think about going in and digging those out. By the way, the remedy is, I'll kind of give you guys a punchline, is all the mud flats in this upper area are going to be dug out. So those mud flats are going to be dug out and replaced with clean sediment because there's just not enough sediment to recover those huge concentrations of mercury. Okay, that's physical transport. I'm going to take a breath for a minute. I'm going to move into something else that's really cool. So now that we kind of have an idea how things are moving, I'll talk about one of the things we did to look at what's happening in the water column. And I was talking to Caitlin earlier about mercury and how mercury moves around in the system, and it is really expensive and challenging to go out and get a lot of water column samples to figure out what's in the water column and what's moving. So I told you a really good story about sediment, and we could really get at that with some relatively low cost and available tools, but increase the level of effort by an order of magnitude to get that same kind of picture for contaminants. So I can say that, and I can say, yeah, this is all great, and we're assuming all the contaminants is on the sediment, but mercury's a lot more complicated than that. It's not just with the sediment. There's methylation, demethylation processes going on, and we're really worried about the methyl mercury because that's where the ecosystem risk comes from. So here's an example of hundreds of water column mercury concentrations. So I have to call it contaminant of potential concern because of legal things. It's mercury. Throughout the system. This is the upper system, that west riser, which is that tide gate I talked about. And here is the Hackensack River right here. And these are reference areas out in the Hackensack River. So these are the mercury concentrations taken over time. And we can take that and say, oh, okay, let's split it out to high tide, low tide. Let's split it out to events where there's storms and not events. Actually, that's already done. The red ones are Hurricane Irene that we had data. But this is log. And you can see at every location, we have 2 to 3 order of magnitude variations. And can anyone draw me a good trend line through that to tell me what's happening in this system? And we can filter this by time, up and down. I mean, we've had like great data scientists look at this upside down, sideways, every way, and you cannot get a good trend to say, oh, okay, this is what's happening with mercury. Yeah, this is what's happening with mercury. So the bottom line is you need really good time series measurements to see what's going on. You can't go out there and just get samples during this event and that event, high tide, low tide, and try to get a picture of what's going. And this represents, I mean, shit, each one of these samples is probably at least $1,000 of data point on there. So, I mean, you could do the math and figure out that literally is probably close to $1 million worth of field effort and sampling. And you can't tell anything from that. I mean, you could tell it's a highly mercury contaminated system, and at some points in time you get up to 10 microgram per liter, which is huge. So we're going to do some optical work to look at. So Brian Bergamaschi, who's actually at UC Davis, worked with another colleague of ours, Emmanuel Boss, who's in Canada at, I don't know, he's Dalhousie, I forget where he is, but came up with a cool technique to use optical proxies for contaminants. So with optics, what are we measuring? I talked about optical backscatter earlier, but a couple of things happen when light shines into water, right? You can get absorption, so it could be a particle that absorbs the light coming through and absorbs specific wavelengths. You could get attenuation, which is basically the net effect of what comes through the water column. You can get backscattering, which is reflecting back at you. So that's when you hit the particles and they're reflecting back, which is basically how we get turbidity, which is probably one of the simplest measurements we're all familiar with. And you get fluorescence. So you shine something with one wavelength, it activates a property in that, and it shines you back at another wavelength. So chlorophyll A is a perfect example of fluorescence and how we can measure something with fluorescence. So we also know that contaminants of concern associate with suspended solids, particulate organic carbon, and dissolved organic carbon. So depending on the different proportions of those in the water column, that's where your contaminants will be. So PCBs in particular are going to be heavy duty on your particulate organic carbon. So what you can do is develop an optical model that uses a partial least squared regression. So it's like a fancy time series principal components analysis for anyone who's into good statistics. And you can start to develop a time trend using optical properties of things like dissolved methyl mercury. So here we have our water depth on the dashed line, and we can get a dissolved methyl mercury concentration. These triangles are data points. So this is the optical model predicting what these concentrations are, and that's a validation sampling event. So it does really good at predicting how these things move around. That's what the instrumentation package looks like. This is kind of the super instrumentation package. You can actually get rid of the ACS on this, which is the big long one right here. So this has a hyperspectral absorption meter, which looks at all the wavelengths coming through that are absorbed and reflected by the water column. We have fluorescing dissolved organic material. We have backscatter, chlorophyll A. The list is basically shines a laser through and does and can particle size for you. So, and I think that's about it. And a big data handler here to collect all the data, and a bunch of pumps and filters to get water in the right places and look at it. So that gets you a lot of information. We've kind of stripped that down. That was the package 5 years ago. We've gotten it down to kind of a mini version of that we're using in the Passaic River right now. But what we can do is now we can look at this particulate methyl mercury signal in the water column. We can go and capture a bunch of samples. So we can get some of those water samples we were getting before, use that to calibrate our optical model. And then go back out a month later after this stuff has been running and look at how well that optical model does. So this is essentially good proof that this works, and it works well. So we get something like 20 to 30 different optical parameters that we feed into that model, and we use it to develop that optical model so that we can then measure basically in real time the methyl mercury, particulate and dissolved, mercury particulate and dissolved, PCBs particulate and dissolved, which is something that no one had ever been able to do before. So that was cool. We just actually got 2 papers published this year on this one. So this is really neat stuff, and anyone who wants to dive into the details, I'm happy to do it and pass on the papers, because that's really bitchin' stuff. So what can we do with that, though? Why does that matter? Why does it matter that we could do that? So here's our precipitation. We have a couple of rain events. We'll talk about the importance of that in a minute. Here we have our tidal signal in the black. So you can see neap up to spring tide, back to neap and up to spring. Salinity, of course, you can see that following. We have high salinity, the rain events come, salinity drops, starts increasing again, rain comes, it drops, and so on. So let's start looking at some things we get from the optical properties. First off, TSS, so we could get that from our backscatter. So we can see a diurnal signal in our TSS, and we talked about that. Now you guys are experts on shear stress and know why things are resuspended, and more importantly, experts on fluff layer. Please use that word. So you can look at the resuspension there, higher resuspension during our spring events. We get some peaks during rainflow, but then kind of clean water right after that, and then a peak during a rainfall. Same thing, another peak during a rainfall. So it's pretty logical to expect after you get a big rainfall event, that actually, so what happens when you get a big rain? It's kind of cool. It washes the fluff layer out. So you actually have lower TSS for a while until the fluff layer builds back up due to autochthonous production. So that was a cool story. So I'm much more on the physics guy, so I really like this stuff. But what picture can you get on the contaminants? So green is PCBs, blue is mercury, and red is methyl mercury. So we can see those following a very similar trend. And of course, when we get a big pulse of sediment, the contaminants follow. We get big contaminant concentrations at the same time. And then they actually follow suit as well. So we have cleaner water coming in, that fresh water coming in from the uplands. It's clean, it doesn't have a lot of contaminants in it. But interestingly enough, those contaminant concentrations build back up as we're building up our fluff layer again. There's a little bit of a lag here that you can't see. So once that fluff layer gets back into the sediment, what happens, that organic material kind of absorbs some of the contaminant from the sediment bed, and then you have your fluff layer is now contaminated. And then it gets blown out, bam, same thing over time. So this is really cool. Like no one had ever been, you would have to get, this is, I think we even calculated, this is like 6,000 data points. So you can do the math, 6,000 times 1,000, how much that would cost. Actually, it would be 1,000 basically. No, it'd be, you could probably get all three done for 1,000. You could probably get a lab to do you a deal, but that's a lot of data. That's huge. So anyway, good stuff. What was I going to say on this slide? I'm going to pause for a minute because I was so excited about that last slide. Yeah. Yeah, here we go. I actually had notes for myself. So one of the things, this is the upper system. So now we can look at the platforms up here. This one is here, this one's here, and this one's down at the mouth. So a big thing we want to see is the influence of storm events, because also determining where you want to clean up is how susceptible are some of these areas to storm events. It could be great if you deposit 2 centimeters of sediment in a year, but it's useless if you have a storm once every 2 years that blows out 2 centimeters of sediment. So we're trying to look at areas that were at risk during storm events. So during storm events, not surprisingly, down at the estuary mouth, you don't have much resuspension. These are TSS, and this is TSS, and a running average tidal day TSS. So we don't see much of a response to big storm events in the lower system. In fact, even stuff in the Hackensack River that's coming through, we don't really see much of a signal from that. As we move up, that signal gets bigger and bigger and bigger. So those storm events from the upland perspective, where we have high flow rates coming in from those tributaries, is where we see a lot of resuspension and a lot of sediment moving around, reorganizing in that upper system, but not so much with the lower system. So again, this gets to that middle system natural break, which is honestly a really good thing because it allows you to kind of start to draw a boundary on an area where you want to get in and do an active remedy, and start to say, okay, it's pretty safe if we leave this area alone and don't get in there and start monkeying around. So, and that's it. So one of the big things, stable long-term morphology. Those Phragmites marshes are stable, they're depositional, so that's a good thing. And then we see localized areas that are subject to sediment reworking of the top few centimeters. That's a fancy way of saying the storms have a big effect in the upper area on the order of a couple of centimeters where you can really move a lot of sediment around, but not so much in the lower area, so near high flow and upland runoff. But there's a big difference between the upper and lower system, and that's actually really cool. That's kind of a neat thing to see, that break between estuarine influence and the upland influence. And that was just an afterthought. That's kind of a meaningless statement. Just as a note in presentations, don't throw meaningless statements on your slides. There's really no need. But we developed some really cool new technology. And ironically, that's what I was saying. You know, I do a lot of work on the government end and research. I mean, we get a lot of, we have some NSF projects we're working on too with Stanford in the Bay. But, you know, ironically, this industry-funded study got us, we have like actually 4 papers published on this site alone and found so much cool stuff because of the data density over a couple of year period that we're able to get, and came out of it with a whole new way to look at contaminant transport that people had kind of scratched the surface of and done the proof of concept. But by no means are we taking credit for inventing anything here. But by being able to apply this, like no one's ever looked at PCBs at this level before. They had looked at mercury and methylmercury, but again, over like a couple week period, we had systems out over many year periods. Maybe I could show you data till you're blue in the face, but it's surprising, you know, and that's one thing that's kept me involved and engaged in a consulting career. I mean, I guess I'm making a push that, you know, those of you when you graduate and get done, like there's so much cool stuff to be done out there, and there's like every avenue to finding neat problems that you can solve. So, and yeah, we find new ones all the time. Anyway, thank you guys very much.
I think you said this, but I missed it, and I thought your calibration of the mercury with the optical instruments was really cool.
Mm-hmm.
And were you able to do a direct correlation with one optical instrument to make that, or did you have to use multiple different types of optical measurements to come up with that model?
Multiple measurements, so.
It's not just like directly correlated to particle load or something.
No, and actually that's a very good question, because sometimes for like snapshots of time, you can say TSS and PCBs are highly correlated, but you get some shift, whether it's seasonal or the freshwater flow comes through, and that relationship totally changes. So it's a combination of variables, and I like to think of it as kind of an optical fingerprint. So there's 26 parameters that are measured optically by that big beast system. And it's everything from, you know, slopes of different parts of the adsorption spectra to chlorophyll A, TSS, all the other parameters you can think of off the bat. But there's a lot of parameters thrown in the bucket with that partial least squared regression. So we're actually not guiding it. It's a purely statistical model, which scares the shit out of me sometimes, but it works really well. So there are some underlying physical relationships between like the dissolved organic carbon and that particulate concentration that are unique to the PCBs that are absorbed to those sediment. So the way I think about it is when you're suspending sediment from an area that has a high contaminant load, it has an optical fingerprint. It's different from sediment coming in from the watershed or sediment coming in from the estuary. So the optical model can detect, if you will, the fingerprint of that load coming that's associated with contaminant.
So would that work in a different, like do you have to recalibrate it based on where you are in your estuary, or could you take that same model into a different estuary, or would you have to recalibrate it?
That's an excellent question. So these are 2 different locations, and they do in that estuary, and they do have different calibrations. So they are built slightly differently. So each one requires its own calibration. We've done another site in the South River in Virginia that's another lovely mercury contaminated site, but it's a freshwater river, unidirectional, and we still got really good calibrations in that site. And actually we're able to see diurnal resuspension of sediment due to crawfish in the system and mercury in the water column associated with that. And that's one of the other papers that's really killer. So yeah, we've been using it in many different systems, freshwater, tidal, but yeah, it seems to work really well. It's a very robust approach, but it does have to be calibrated on a site-specific basis.
Yeah, so that was a lead-in kind of to my question about, you talked about the mercury signal in the dissolved system, but what about the organic matter that's macro, like macrophytes or the Phragmites contribution, and maybe does that show up in the
Autochthonous.
And the fluff layer? And did you measure that? Because in your $1,000 or $1 million samples, what?
Not mine.
From the system.
Yeah,
So
in here.
much of that was sediment or water column? Versus
No, this is all like micro. It's all probably below 2,000 microns. So that's a good question because one of the teams that was working on this with us did go out and sample like Phragmites leaf litter and looked at that. And what they found is when it's fresh, it doesn't have any mercury associated with it. As it breaks down, as it undergoes diagenesis essentially in the sediment bed and becomes broken up into little bitty particles, that's when it can absorb mercury from the system and becomes a part of now what we're seeing in these optical signals and these smaller particles. So yeah, that's a really good question because it came up on the site of, okay, well, you see these big rafts of Phragmites floating around. It's like, how much mercury is in those? Because that's a lot of mass. And it turns out not much at all. It's when it breaks down and becomes a part of the fluff layer that it starts to get into play of moving mercury around. Yeah.
So here where the TSS is lower, that's where the fluff layer is filling, correct?
Exactly.
Okay.
So that would be the fluff layer is washed out, and now we're building it up with inorganic and organic sediment. But so, and back, I think you had part of your question was about the fluff layer too, but we don't have any specific samples of the fluff layer because it's really hard to get just the fluff layer without getting kind of the more consolidated sediment. We're talking millimeters, and that would be a whole separate study. And so people kind of played around with it, but we couldn't get anything reliable. It'd be really interesting to see what the organic content and mercury content of that is over time. So frankly, this is kind of a proxy for what's going on in that fluff layer, but that fluff layer is a big key to the cycling of this system.
It seems like you have a higher percent methyl mercury around July 24th, later in the, and I'm just wondering if you have this buildup of a fluff layer, do you have more anoxic sediments below it, and then you get more methylation? It's really interesting to see that change.
Yeah, that's a good question, actually, that I'm not going to get an attempt to answer. Yeah, there's a lot of, there's so many processes going on at the same time. It's really, you can't, every time we would come up with a hypothesis of what's going on, we could shoot it down with another hypothesis, but there's so many non-unique solutions as to what could be controlling the maximums and the buildup rates. Like this slope right here, interestingly enough, is about the same on both of these, and that's telling. I mean, it's like, okay, the fluff layer, regardless of the size or rain event, and that was 2 big rains of it, so you could argue that's like at least twice the volume of rain of that. We still have the same buildup rate of the fluff layer afterwards. So yeah, there's probably 5 more papers in this stuff for someone that really wants to dive in. Yeah.
So after you came up with this understanding of the system, what's happening at the site? I mean, what's the next step? I mean, what did you learn? I mean, based on what you learned, what's your recommendation?
Luckily, I got to write papers and walk away, but no, I'm kidding. So this all went into in the part of the Superfund process, this went into what's called a remedial investigation. And part of that remedial investigation, you try to find all the pathways of contamination to different receptors, being the marsh birds, fish. So we were trying to find out the direction of mercury motion and where it was going, and then how stable it was in those areas once it got there. So that information went forward into a feasibility study of different remedies. So then a bunch of different remedies were looked at and kind of conceptually studied over which ones would reduce risk the most. And that's been produced, and right now the remedy is being designed for where do we go and take out the honeypots of mercury, if you will, to shut down this system of mercury transport.
The lower part of the watershed should be just left untouched and just work on where, the upper part.
Exactly, and that's basically what's happening. So that finding alone kind of gave the justification for, or gave the basis, I don't want to say justification, gave the basis for the design, the remedy design. I mean, afterwards we sound really smart because we know it all, but in the beginning it was really, like, we had no idea what was going on in this system.
You're going to scoop out the upper soil, and you're going to just take the whole thing.
Pull up a good conceptual diagram so I can talk to it a little bit, because that's a good question. There we are. So I was showing earlier that a lot of the high deposition rates are on these mudflats, as well as the high levels of mercury. There's mercury down here, but not as much. So these are critical areas. This is where a lot of the mercury was trapped. There is mercury in the marshes, but lower concentration. So these mudflats are kind of the centers. What happens is during big storm events, you can erode sediment from those mudflats as well. They build back up quickly. I mean, they're very stable and net depositional, but those are acute events. So in the upper system with the highest concentration, they're going to go in, remove these mudflats, rebuild them with clean sediment, and do some removal in the very upper area of some of the channels, but the channels are basically to stay away from. One of the dangerous things in these systems, if you go in and start monkeying around, and again, Elkhorn Slough is a perfect example, if you start monkeying around in one area, the whole system will feel the effect. So that's why I started kind of in the upper area and slowly working down, and then going to monitor that and see what happens. And if it's not cleaning up with the trajectories that we hope, then they'll move further down the system.
Asbestos. I mean, once you start touching those things, you're putting things in the system, and it might be worse than you're trying to fix.
Absolutely, absolutely. Especially, I'm going to go back to the picture in the very beginning, just so we can all kind of conceptualize it, although I'm sure everyone can. Whoa, am I going the wrong way? So that first picture I showed, right here, I mean, these are the mudflats we're talking about. So the dangerous part of that is, how do you get into the, and you saw how wide those Phragmites marshes are. I mean, we're talking hundreds to 500 meters. I mean, that's like football fields of this dense marsh. So how do you get construction equipment in to do removals and backfill in that? I mean, you got to do something. So that's part of the remedial design, is not just what do you do, but how do you do it without destroying the whole system.
Well, thank you, Craig. Let's thank our speaker.
Thank you, guys.